Morning. Can you hear me?
Yes,
All right. So how many of you are? There are only two. Okay, we'll wait for another minute or two.
it's Friday. Everything takes long on Fridays.
Oh yeah, it's Friday. Yeah. It's Friday. Oh yeah, the people are coming in. So the ones who are in by now, do you have any questions regarding the matter, regarding the stuff that we did in the last 2 days? Right. I have uploaded the slides on Tuvel for the past two lectures. So I have uploaded the introduction and the least squares. And today or over the weekend, right, I'll upload the neural network stuff as well. All right. We'll wait for another few minutes. All right. Welcome everybody. So today I want to continue with the neural networks. So just to quickly repeat, to do the quick overview, what we've done in the last 2 days this week. So first we did the least squares. Then yesterday we looked at the singular value decomposition and the pseudo inverse. And we looked quickly at the example how the pseudo inverse improve the stability of calculation. Then we looked at the basic neurological biological neuron. We looked at McLaughlin-Pitts model. We've seen how the boys developed the mathematical model of biological neuron in the 40s of the last century. We looked at the learning, so how this very simple neural network can be trained. We used the chemotaxis algorithm to demonstrate the parameterization in the learning. And I have explained some tricks regarding the thresholds and activation functions, right? So what I want to do today, is just to highlight some types of the neural networks. One of them would be a multi-layer perceptron and the radial basis function, a neural network. And we're going to take a look on some aspects of learning. So that means of the parameterization of the network and the structure selection of the network. So did any of you, does any of you have experience with, for example, multi-layer perceptron or radial basis function? Did you use them in the past? Do you know what it is? Do you know how to use it, and what did you use it for? Come on, anyone? No, no, no. No. Okay, right. So let's take a look. Let's take a look on the sketch. What we did yesterday. So, and on this screen, what you see is the derivation of the biological neuron as we did yesterday. So on the top here, right? Just give me a second. Is it working? Yeah, it is. So this was the simplest possible neural network that we derived yesterday. So if we extend that network to a multi-layers, so to extend number of parameters and number of interconnections in between them, then we get so-called a multi-layer neural network. So this side, on the side of the inputs, we call it the input layer, and on the side of the outputs, we call it the output layer. And everything in between, they're called the hidden layers, right? And this can be represented in the literature as you can see here. So we have the input layers, we have the output layers, and we have the many hidden layers, right? So that's it is all about when you see the kind of a sketch of the neural networks, right? So we have the input layer, and then in intermediate hidden layers, they are interconnected between themselves the way as they are connected. So they can be a different type of connections, and the activation functions can be different. So basically depends how many layers do we have. This is then called how deep the neural network is. If you have only one layer, right, it is one layer neural network. If you have 20, 50 millions of layers, right, it's kind of a multi-layer. And this training of that kind of a neural network is relatively complex thing to do, and that's why it's called the deep learning, right? And nobody really understands how what is really the process in the deep learning, right? So that's why everybody is so skeptical about the artificial intelligence and all this stuff, right? Because nobody really in detail understands how the parameters of the neural network, right? When the neural network is complex, how the parameters really get trained. However, right, in some cases, people say in many cases, but not in many, but in some cases, the performance of that kind of neural networks are very impressive, right? So that's why there's so much fuss about it, about the artificial intelligence, deep learning, and so on and so on. But I mean, yes, the things are complex, but from the, let's say, theoretical and basic perspective, they're not. And this is what I want to show today, right? I want to explain the basic structure of the neural network, and then you will see that this is no bow. It's not a big deal. It is just complex. That's all, right? Now, do you have questions up to now? Do you hear me well? Do you see the screen well? Yes, I guess that you see screen well and that you hear me well. Do you have questions? Okay. Right. So now we are going to go through some types. Well, actually two types of the network. Right. First would be a multi-layer perceptron, MLP in short. Right. The multi-layer perceptron is a multi-layer neural network. Right. Which has a connections between the neurons, and the activation function, right, can be a different ones, right? They can be sigmoid function, linear function, it doesn't matter. So on, or many others. In many cases for the multi-layer perceptron, we have a sigmoid function, the one that we have looked yesterday, the one that looks like that. We can use the linear functions as well, right? And the parameterization, it's then based on the weights, right? So the same thing. So yesterday, what we actually done, we did the most simple, the simplest multi-layer perceptron. So now, if we just if we take an example, we are going to just try to model the function, right, shown here. So some nonlinear function with the multi-layer perceptron with the number of the neurons, right? So I'm just going to reproduce these plots in MATLAB. So if you do the plot of the function with the how many, with the two with a single neuron, right? We would get approximation like that. If we extend the network a bit, right, with the two neurons, we would get a better approximation. But we still see, right, the two neurons would not be able to model all the complexity. So we extend it a bit with the 5 neurons, and then we see we get the perfect match of the function we want to model, right? If we do it two-dimensional function, right, with the multi-layer perceptron, the same thing, right? With the single neuron, we will not do the good approximation. We would get something, but not much, right? With the two neurons, the approximation gets better. And with the 5 neurons, we get a pretty much good approximation between the actual approximation of the neural network and the real function, right? So as you can see, these are only toy examples, because in reality, we don't really have the real function, and we just have a data, and then we need to fit the neural network to a data. Okay, so now another type of the neural network would be the radial basis function network. So this, I mean, remember this one, right? Because this is the neural network that we're going to use through the entire lecture, not really into as an example, right, as a tool, but as a comparison to other techniques, right? So I was then spent some time now explaining the radial basis neural network, right? So some properties and some, let's say, some things about this particular type. So the radial basis function neural network is also universal approximator. So that means with enough neurons and with enough parameters and with enough connections, we can approximate any function we want, right? I mean, seriously, any. It only has one layer, right? So the input layer and then a summation block, right? So input layer we have here, and the sum of the neurons is our output. The activation function of the radial basis function neural network is some sort of the Gaussian type of a function, right? So Gaussian Bell. And the activation function is parameterized in this case, right, in any RBF case, with a center, where the center is, where the actually center is positioned, right, with the width of the Gaussian function. So this one can be actually smaller or bigger. So that means that the activation function is more spread or is it thinner, and with the actual weight. So that which means how kind of a tall the function gets, right? If we take a look, the two-dimensional approximation, two-dimensional representation, so x, y, z, three-dimensional, I mean, that would look that the Gaussian bell would have a kind of a shape of the surface, right? And the weight would actually mean how much do we lift this Gaussian type of the surface up and down. So imagine that we want to approximate the surface, nonlinear surface Z, right? And now this is the single neuron approximation of that particular surface. If we want to have a better approximation, we need to place many of those Gaussian bells around it, right? And lift them up and down in the way to be able to touch the surface as accurate as possible. Now, is this clear? Do you understand what I'm talking about? Right? Does what I've just said, right, is it complicated? Do you understand it? It's not. But what I've just said, it really isn't complicated if you look at it from another perspective. Now imagine this neural network, this radial basis function neural network, as a toy that my daughters are using constantly. So have you seen this before? This kind of a toy which has a pins, right? And you can actually make a print in those pins, right, of your hand or your face. Have you seen that before? Have you played with that? Do you know what I'm talking about? Right. So now this is an analog radial basis function neural network. So think of them, think of the each pin here as a center, right? So as a position of the center, this one, right? And now the width, the sigma, the width of the Gaussian bell here would be constant for these pins, and it is just the thickness of a single pin. And how much do you need to lift it up and down is a weight. Okay, so now you can think of the lifting the pins up and down. So basically making a print of your hand or your face or whatever you want to actually print on this toy. This is then learning. This is a parameterization of the neural network. And now imagine if you have those really lot of pins, right? And if those pins are kind of a thin, so that we have a resolution which is big enough, you can really approximate any type of a surface you want with those pins, right? And lately, I actually found a YouTube video which shows you some tool that you can buy, and this actually really is the utilization of the analog radial basis function neural network. And now do you see the, okay, just a second. Do you see the video? Right. So now you see, you have this tool, right? And then if you want to actually find out how to cut the tiles. So that means this is the surface that you want to approximate, or the curve, right? And by just lifting the pins, right? So that means the Gaussian functions, right, up and down, then you can have a surface, right? And then you can copy that particular surface to a tile, and this is now how you actually used the neural network for the tile cutting. Is this clear? Now, when you have in mind that really simple representation, right, what the neural network actually does, right, you will see that you should really not be afraid of the artificial intelligence so much. So basically what the neural networks do, they approximate some sort of the function, right? And how to do that, this is a matter of learning. And how well can you approximate something, either the surface or decision making or whatever, depends purely of the complexity of the network, right? Imagine if that tool for the tile cutting, right, if it is longer, right, then you could actually copy bigger lines or bigger surfaces, right? If the pins are actually bigger or smaller, that depends on the resolution, and you would get as the copy as good as you want. Okay. Now let's just go further. So now the same thing, using the radial basis function neural network, right? We can approximate the surface with the, so here's the approximation with the 3 neurons, right? With the 5 neurons and 31 neurons. So we can see, so extend the number of the neurons, the resolution gets better, right? And the ability of approximation of the surface gets better. Now the question is up to the what level, right? So the question is, if we extend the number of the neurons, will we always get the best, the better surface or function approximation? Okay, so now I want to actually want to explain a little bit more, right, about the training of the radial basis type of the neural network. And the easiest thing to do that is just to use an example, right? So what we can do with the network in this case is that we have number of the neurons. Each of the neuron is represented with some sort of a Gaussian function, right, which can be positioned in the different places around the operating region. It has a different width, right, and it has a different height, and a sum of the neurons, right, is then our resulting function, which is purple in this case. So if we take a look now quickly again the structure, so what we have the neurons, which has the different parameters. Each of them has a different parameterization, and then we have the inputs, and the output layer is created just by the simple sum of all the neurons. And this is what we see on this particular picture. Now, much easier is if I demonstrate that on the example. So now, this is our, as I said before, our neural network, which has 3 neurons, blue, red, and yellow, and that the resulting kind of a function is a purple. So now what happens if we move centers, and if we change the widths, and if we change the weights? So now in this animation, it shows us, this animation shows us, so basically what happens is that the widths and weights and the centers, they just move kind of, not really randomly, but up and down. So by the moving of the neurons, right, by the changing the parameters of the neurons, we see that our purple function, so that means resulting function, changes significantly. So with the correct position of the centers, with the correct choice of sigmas, so that means widths, and the correct choice of the weights, we see that the purple line can model quite complicated lines. Do you agree? Right? Do you understand what you see on this animation? Right. Okay. Now imagine, what do we need to do now? So if I have some data points, right, that we want to match, what we can do, we can build the simple training algorithm as we did yesterday. So the chemotaxis algorithm, which changes the widths, the widths, the weights, and the position of the centers, right? In order to fit the data as good as possible. And this is demonstrated here. See, we have the green is the set of data, and we have selected the number of neurons of having 3 of them, right? And then utilization of the simple optimization algorithm as yesterday, chemotaxis, right? We see that our resulting function, so the purple one, fits data quite well after the training is completed. Right, I'm going to run that again. You see? So the widths, the centers, and the weights, they move randomly, and then slowly they fit to data. So what I can do is, I can select the number of the neurons, so number of centers. So now we have 3. Let's take a look what happens if I take 2. See now, the two neurons, 2 Gaussian bells, wants to get positioned in that way that they fit the data. And we see that this is quite, that only with the 2 neurons, we can model the set of data we have quite okay already, right? By increasing the number of centers, we had 3, for example, 4, right? What happens now? So we get the functional approximation, which, right, in theory should be better than the one with the 2 neurons or with the 3 neurons, right? Now, what happens if I increase the number of neurons even more, for example, to 6? What do you expect? Come on, what do you expect now? Anyone? Better approximation. So first of all, what we realize here now is that, so let's do it again. For example, let's do again, let's do 5 neurons. So what we see is that it takes optimization, it takes longer, because it needs to it needs to optimize, it needs to find more parameters. This is one first observation. Second observation, the more of them we have, right, the blue line, so the resulting line, approximates data more accurately. So that means it's more rigid, so it actually gets more flexible. Now the question really is this good or bad? Because we don't know this data, for example, here and here. Is this due to the noise? So that we have, for example, the bit here. Do you really want to model that? Or are just those 3 data points kind of corrupted by noise, and we would like to have the curve, right, resulting curves over here, right? So this we don't really know, right? But with the extended numbers of neurons, we get ability to approximate more, let's say, flexible, more complicated curve. So only with the 2 of them, right? The 2 of them, they're definitely, we're not able to model those bumps here. We will get some sort of the averaging in this area. So the curve gets fitted somewhere in between as good as possible. Now the question is this good model or not? So here in this area, it seems to be. Now the question is, do we want to model that part better or not? If we don't, 2 neurons is fine. If we do, we use, for example, 5 or 6. So now I am going to extend the numbers of neurons, for example, to 10. Right? Now it takes, first of all, it takes longer. And there's another thing that we observe here, that some of the actually weights are negative. You see? So not all of them are positive, but with the extending of the number of neurons, right? Some of them, in this case, 1 goes to the other direction. And the neural network wants to actually approximate, wants to fit the curve through as many data points as possible. So further increase, for example, 20. So what happens here, right? More and more neurons, right? They go to negative. And if you take a look, right? So I'll try to increase that even more. Just a second, I want to check something. So what happens here? So when we have a really lots of neurons, actually, now in this case, the neural network wants to actually fit, right, each neuron to a data point, each data point. And if increase them even more, right, we would get the, let's say, some sort of approximation, but the question is which one is better? Is this clear? So it is clear now that it is up to design, or up to yourselves, right, to choose the number of neurons, and to choose, right, with the number of neurons, right, we choose the structure of the network. So the more complicated it gets, right, we get a better approximation. However, it takes longer, and it is not sure with the millions of the neurons that we would get much better approximation. So there is always a trade-off, right? So if we go questions, do you have questions up until now?
I have a question regarding the training of this network now. Did you use the stochastic jumping? Did you decrease that over time here, or did you keep it constant like in yesterday's example?
It is exactly yesterday's example, right? it is only what it is that it is vector based, so that basically I change the algorithm is the same as yesterday, right? We can take a look, right? So we get the initial values, right? So initial values and sigmas, and the algorithm is exactly the same, right? Has no difference. So it changes slowly, randomly, and so on, right? But the point is, I mean, what I want to show here is the structure selection. So what the number of neurons does to approximation, right? It is not always the case that if you choose 2 million of them that you will get the good approximation, right? There is a certain number, the certain structure of the model which is best, right? Which we will see later, a little bit later as well. Any other question?
Yes, I got one.
Yeah.
As one can see in the figure, many RBF functions are negative and positive with the same magnitude, we could say.
Yeah.
Wouldn't it be better to use a regularization term to just pick the good parameters we need so that we can hold?
Yes, and this is what I want to show now in the next examples. Now, you mentioned the regularization, right? Explain in your own words, what do you understand with the regularization? Where did you hear about the regularization, right? And how do you know about that?
Basically, don't know if you knew the book Neural Networks from the Princeton Free Press.
Yeah.
I've read the book, and regularization is basically you add the parameters to the cost term.
Yeah.
And also optimize for the parameters so that you don't get big parameters and small parameters, but get them in the same range, let's say, so that you don't have runaways and small parameters.
Okay, exactly. Now, this is what I want to now try to explain till 12, right? So my goal for today is, if I explain regularization well, right, I would be much happier person for the weekend. Okay, so the regularization means that the weights, right, or the parameters being really big or really small, right, is something wrong. So regularization means to kind of prevent the weights being very high numbers and very low numbers. So that means that they cancel each other out, right? This is bad. This is wrong, right? And we have to do everything that is in our power to prevent that. And I have a further now example in which I will try to explain just this. Okay, so now first, in this example that I have just shown, we optimize the widths, the weights, and the centers. So we thrown the number of centers on the initially, some randomly, we just thrown them on the operating space, and then let the optimization algorithm to optimize all these parameters to fit the data. This was one of the approaches. This approach is in reality good. In theory is good. However, when you have the neural network, when you need to train 2, 3, 5 millions of the neurons, which is in many applications the case, right? As soon as you go and start the neural networks for the image processing, you will end up with the trillions and the millions of neurons. As soon you need to optimize to train the parameters of the network with the classic standard optimization routines, the ways I showed you, right? you will end up, it'll be just too slow. It'll take years to do it. So many effort has been done how to reduce the computation cost and how to find the good ways of parameterization. And one of them, right, is suitable for the radial basis function neural network, in which we can find the weights. So that means how high the Gaussian bells are with the single regression step. So we use a least squares to find the weights. So now, or before, we use the optimization and the things went right, and then it was found. But now there is an approach that we can find it in the single step. So basically, all the weights get found immediately. And if you write down now if you take a look of the neural network kind of equation, right? For the 3 neurons, we see we have one weight here, one weight here, and one weight here, right? And we have the centers and the sigmas, right? Centers and the sigmas, centers and the sigmas. So now what we can do, we can fix the centers, right? We can place them across the operating region equidistantly. It doesn't matter how, we just place them and we don't optimize them. We don't touch them. So we place one here, one here, one here, one here. And then we can also decide that all the widths are a constant value and we don't optimize them. We just set them, right? Something to 1, 7, whatever. And then we try to find out the weights in the way that the weights, the approximate data as good as possible. So if you write the neural network in the equation like that, right? And if you have the set of data, then what happens is we go and we said for each data point, we write down the equation of the neural network, right? Like this, for first data point, second data point, and the last data point, okay? We can, where the y, so the measurements of the y are here, right? And x's are here. This x1 is the first data point, right? So if you have the data arranged into the matrix. So first xy data point, second xy data point, last one, and they go like that. So this is the first one, and here are the x's. If you do that, we can write the entire thing in the matrix form, right? So the measurements on this side, right? And inside of the phi matrix, and the vector of parameters theta, or that we're looking for, is here. Is this clear? You understand that? All right. So it's a matrix representation of the network. So then we end up with the least squares equation, with the standard linear equation, which is the system of equations is linear in parameters. And in this case, we can then use the least squares regression in order to find the parameters. Is this clear? Come on. It is important now for me to understand. Do you understand that or not? Right. So now, here I have the one run where we just placed the centers equidistantly across the operating region. So one is here, one is here, one is here, one is here. The widths are set to some constant value, some OK value, and then the weights were calculated using the least squares, and this is then what we get. Right? So we get the approximation of this. So again, it's not the best approximation, but it is much better than nothing. And it takes, look, It takes that much, right? So immediately it's done. So now if I change the number of centers instead of 4 to, for example, 2, right? So I don't move the centers, I don't change the widths. I just calculate using the least squares, right? We just calculate the weights. And here is approximation with the 2 neurons. So it's not, obviously it's not good. If we increase the number of neurons to 5, we get a better approximation. And we use here, as I said, the least squares algorithm. So the least squares algorithm is actually embodied in this particular function, which I'm going to open. So I am using here the theta, which is theta number 2, which is using the standard least squares algorithm. Okay. Now I am going to increase the number of neurons even more, right? To, for example, 12. Try that. So now 12 is too much. So we'll do it 5 again. So what we see here, we see that with the 5 neurons, we get some sort of approximation, right? And we are realizing that some of the weights, some of the kind of weights, they're negative, right? And so actually 1 in this case, so 3 of them, 1, they're positive. So increase number of weights to a number of centers to 7. So now what happens is that some of them are positive, some of them are negative. However, our approximation looks better. Well, it looks something. Now, and let's say the maximum weight here in this case is close to 3, and the minimum is also minus 2.5. We increase the number of neurons again to even more. So what we get approximation again, right? Here, which is now, this is actually very good approximation, I would say. Okay, see this one, like this. However, look at the weights, right? They go to up to thousands, in the regions up to thousands, right? The plus and minus, right? So that means they cancel each other out. And we get, it seems that we get the good approximation, but this is because the weights are so very big and very small, right? This is not a good approximation because we actually starting to overfit the data. So that means that the neural network wants to fit each neuron exactly to a data point. And this is not good. Is this clear? Right. So what can we do? What can we do in order to reduce or to make things kind of better? Now here, the singular value decomposition and the pseudo inverse come into place. So I will instead of using the exact calculation using the least squares, I'm going to use the pseudo inverse, right? The pseudo inverse with some level of tolerance. And so I'm going to use the theta number 3. And in this case, what we see, right? So the pseudo inverse it will cut down the singular values which are close to 0. It will round them to 0. And it will use only the high singular values. And this results in the parameterization, right? So finding the theta parameters, so that in this case, the weights, which are more stable. So that means they are more, they're in the same range. So if you remember the picture from yesterday, the two constant values instead of the different different parameters, right? And in this case, we get now a good, better approximation, right? I mean, still some sort of approximation, but look, actually the level of the theta, right, of the weights, it is not in the thousands anymore, but it is reduced, and all of them, they are more or less in the same range. So this is what you said before. This is a regularization, forcing, right, or making sure that the parameters do not go bananas, so that they're not too big and they're not too small. Is this clear? Okay, so we have another, what, 7 minutes. What should I do now? Yeah, okay, let's continue. So now what I can do, I can now, instead of just calculating the weights of this particular neural network, what I can actually try to find out, not using the optimization, but to change the sigmas as well. So assume an example that we have the number of neurons, I don't know, 3, 5, whatever, and then that we select all the sigmas to be equal to a one number, but that all of them that we change at the same time. And then we try to see, right, which ones, what kind of a neural network will that produce. So let's take, for example, a 4 centers, okay? And we change the sigmas, right, from very, very small number to a very high number. And we will use the theta, yeah, okay, this one. So here what happens, we get the, we just change the sigma from the very big number and very small number, and we take a look at the cost, right? So we see that the sigma, when we use the sigmas, which are the, I don't know, around 10, right? So basically we change the sigmas between 0 and 100. So when the sigma number is around 10, no, 12 or 15 or something like that. So around 20, for example, we see that the network does not get improved anymore. So here the choice of the sigma would around 20 would be a good choice, right? So now that means we have the 4 centers placed around the operating space. We have selected sigmas, which would be around 20, and we calculated the weights using the least squares. Now, what I want you to do is take a look here. During the calculation, right, we were kind of warned, right, that the condition numbers, so that means that the singular values, they get close to 0. So that means the using the least squares algorithm here gets into trouble. So let's then switch between the least squares algorithm and the pseudo, using the pseudo inverse, like that. And let's run that again. So now we see that the calculation of weights is then get regularized. So that means they cannot get too big or too small, right? And then in this case, then the selection of the correct sigmas would be different, right? And we can find exactly the correct value, which would be here around 26. So the moral of the story is the regularization here is very, very important. And the same thing, I'm going to do that when I want to optimize the sigmas, right? So what happens here? Do you follow what I'm doing now, or are you getting confused? Come on. Are you still there? Okay, all right, so I'll do this example and that's enough for today. Right, so now what I want to do, I want to calculate weights using the least squares, and I want to optimize the widths, the sigmas. And let's see what that happens. It breaks. No, it doesn't. So basically with the 3 neurons, right, which are placed around, I can get the approximation quite okay. Again, I get the warning that using the least squares is not really a good idea to use, so that the pseudo inverse should be used. So, and I do that now with third. So now in this case, we get the actual, probably a better approximation. But the thing gets really interesting when we choose a number of centers, for example, a large number, let's say 10. So this is now the network, right? Found approximation with the optimized sigmas and the widths found by the least squares using a pseudo inverse, right? And it is quite okay. And we have all the weights in the same region. If we used the ordinary least squares, right, the weights would actually go crazy, right? They would go into the crazy numbers. So the moral of the story is regularization is of extreme importance, and it is up to you, up to the people who are modeling, right, to take care about the regularization. What the difference between lines are? Which one? Which one do you want to know? Between line search, which one? So tell me, look, do you see that here? Which one do you want to know? A1, A2, A3, or A9? The difference between which ones? This one. So this and 2. I did not run this one, right? The line search algorithm means that we just try all the things. So that the parameter changes from small to a big number. And in this case, right, line search sigmas, we are looking, we are just looking for all the sigmas, right, for the small and the big ones, right? And in line search C sigma, we do the line search on the centers and the sigmas. They're just more complicated. So like that. So the position of the center, so the number of centers change and the sigmas change, right? And we are doing the calculation of the weights using the least squares. And you see every now and then we get the warning that the least squares algorithm is actually badly conditioned. And what we will now see, we will see that the weights, right? So that the weights get some of them, I don't know, I'll see which one I'm using it right now. It's regularized. Okay, this one is the one which shows us the maximum weights using the pseudo inverse. And we see that the maximum actually weights are, let's say, around 20. And if I use without it, I can, they will go crazy. So if I use this one, number 2, and now they will go, no, they will actually break. Okay, so what I want to mention here is the regularization is of extreme importance. It is up to the designer, so up to you to use it. And the singular value decomposition and the pseudo inverse with the set of a tolerance is an effective tool for regularization for when you want to find the parameters of the radial basis neural network function, right? To find the weights. So it is important to know from today that the extension, so making the network bigger, it will make a better approximation. However, we need to take care that the weights or the parameters, they don't go crazy. Do you understand that? Everybody? Okay, so this would be all for today. Have a nice weekend, and we will meet again on Wednesday. We will finish with this with the neural networks. It's not much left. There's one example which I wanted to show you, which is taken directly from the industry, and this one is actually it's a good one. But now with the neural networks, right, we are close to finished, right? That's everything what I wanted to say about it. It is not that much about how many neural networks do we know and stuff like that, but the things which are important, that when you use the neural networks, that you need to be careful about that. And this is the structure selection, the choice of the algorithm for training, and the regularization. Do you have questions now regarding what we have done today? If not, have a nice weekend. Bye-bye.
Excuse me, one question.
Yeah.
I was unfortunately not able to really participate today. So there's a
Mm-hmm.
question about the recordings of this lecture.
Yeah.
Can I access it somehow?
Look, I said yesterday that I don't know will I put the recordings
Okay,
be
okay,
available
sorry.
or not? But look, this lecture, today's lecture, right?
Mhm.
There is nothing confidential about
Yeah.
today's lecture. There is no industrial examples in this lecture. So this lecture I will put, it will be available, right? But the
Mhm.
yesterday's lecture, I don't know, but the first one probably won't be. Right?
Yeah, okay, understand.
There's some stuff in there. Look, I mean, the point is you will get the slides, right? And from the slides, I will remove everything that must be removed.
Yeah, yeah.
I will take some time at some other lectures, and I will explain what is it all about the undisclosure agreements, right? Do you know what that is? Do you know what NDA?
Yeah, of course. I accept it. It's not a problem for me, this contents, but today I don't know what was really said. So because I just came in a few minutes before the end,
No, okay,
and
no problem.
I just wanted to know if I can hear before the next appointment.
Yeah, okay. I will definitely put today's lecture on. Right?
Okay, thank you
Today's
very
lecture
much.
is not a problem, right?
Perfect.
Okay. Any more questions for today? Okay. Have a nice weekend.
You too. Thank you.
Bye bye.
So
Bye
thank
bye.
you. Bye.
Thank you.